As all your attention span is so low, I am gonna have to put a Subway Surfers gameplay to entertain y'all.
Hey, welcome to The Explainer. Today, we're going to decode the fundamental language of physics, physical quantities. This is basically the code that scientists use to describe everything, from a tiny little atom all the way up to the entire universe. So let's dive right in.
So it really all boils down to this one big question. How do we get past just saying something is big or fast and actually describe it in a way that anyone, anywhere on the planet can understand and check for themselves? Well, the answer is measurement.
So here's what we're going to cover. We'll start with the absolute basics, the building blocks. Then we'll meet the two main tribes of quantities. After that, we'll check out the cool toolkit physicists use for measuring stuff, learn some secrets to getting it just right, and finally, we'll crack the code on the universal language that really ties this all together.
All right, first things first. Let's start right at the very beginning. Everything, and I mean everything, we do in physics is built on this one super simple but really powerful idea.
Okay, so what is a physical quantity, really? Well, it's any property of the world around us that we can actually put a number on. It's the difference between saying, whoa, that's heavy, and knowing that it's exactly 10 kilograms. See, it's not just about looking at something, it's about actually measuring it. And check this out. Every single measurement you ever make has two essential parts. You absolutely need both. First, you've got the magnitude. That's the number, like 24. But 24 of what? Apples, inches? That's where the second part, the unit, comes in this case, N, for newtons. Without the unit, the number is just, well, it's meaningless, right?
Okay, so we know what a physical quantity is, but it turns out they kind of belong to two different tribes, and the difference between them is absolutely crucial. It all comes down to direction.
On one side, you've got scalars. These guys are simple. They just have a size, a magnitude. Think about mass, or time, or temperature. None of them have a direction. But then you have vectors, and these are a whole different ballgame. They have both a magnitude and a direction. A force isn't just a push. It's a push in a very specific direction.
And this is exactly why scalars are so chill to work with. The math is just simple addition. You've got 5 kilograms of apples, you add 7 kilograms of oranges, and surprise, you get 12 kilograms of fruit. Super simple. No direction, no problem.
But what happens when you try to do that with vectors? I mean, if you have two forces pushing on the same box, how do you add them up? You can't just add the numbers anymore because suddenly, direction changes everything. All right, let's start with the easy one. If two vectors are pointing in the exact same direction, you just add their sizes. A velocity of 2 meters per second plus another 6 meters per second in the same direction gives you a grand total of 8. Easy enough, right? But what if they're pulling in opposite directions? Well, now you've got a tug of war. An acceleration of 27 units to the right is fighting against 20 units to the left. You subtract the smaller one from the bigger one, and the result is a much smaller acceleration of just 7, and it's in the direction of the stronger force. See, direction is literally everything here.
Okay, enough with the theory for a second. Let's get practical. How do we actually do the measuring? Well, for that, you need the right tools. And believe me, physicists have a whole toolkit for the job.
So let's just take length, for example. For big stuff, a tape measure is totally fine. But what if you need to be more precise? You upgrade your tools. A Vernier caliper is 10 times more precise than a regular ruler. And a micrometer? It's another 10 times more precise than that. You see that pattern? It's incredible. The smaller the thing you're trying to measure, the more insanely precise your tool gets.
So, okay, having the right tool is one thing, but using it right to get a truly accurate, precise measurement, that's a whole other skill. Now, a tool like this micrometer might look a little intimidating, right? But it's really just a simple process. You combine the reading from the main scale with this super fine rotating scale, and it lets you measure things down to 1/100th of a millimeter. It's just about following the steps, and boom, you get this crazy accurate measurement.
Okay, here's a classic problem you'd find in any physics lab. How do you accurately time something that happens really fast, like a single swing of a pendulum? Your reaction time with a stopwatch is just too slow. You're going to introduce a huge error. So, what's the clever way around this?
So here's the brilliant solution. You don't even try to measure one swing. Instead, you let it swing, say, 20 times. And you measure the total time for all 20 swings. Then you just divide that big number by 20. That little bit of human error from starting and stopping the watch, it gets smeared out over all 20 swings, making it practically nothing. So clever.
All right, we've talked about tools, we've talked about clever techniques, but for science to work across the whole world, we all need to be on the same page, speaking the same language of measurement. And that's exactly what SI units are for.
And the whole system is built on this really beautiful, simple idea. There are just a handful of fundamental quantities, which we call base quantities. Just think of them like the primary colors of the physical world. Every other unit you can possibly imagine is just a derived unit, made by mixing and matching these base ones.
And what are these magical building blocks? It's crazy when you think about it. Almost all of classical physics can be described using combinations of just these 5 things: length, mass, time, temperature, and electric current. It's this incredibly powerful system, all built on a foundation of just these 5 core ideas. That's amazing.
Okay, but what happens when you're measuring something huge, like the energy from a star, or something ridiculously tiny, like a molecule? You don't want to write a number with 30 zeros, right? Well, the SI system has a super smart tool for that: prefixes.
These are basically just nicknames for big and small numbers. Instead of saying 1 million watts, we just say 1 megawatt. Instead of 1,000th of a second, it's 1 millisecond. It just keeps everything clean, simple, and easy to understand, whether you're talking about the cosmos or the microscopic world.
And this, right here, is the final, beautiful piece of the puzzle. How do we get all those other derived units, like for speed or density? Simple. The units literally just follow the math. Speed is distance divided by time, right? So its unit is meters divided by seconds.
Subscribe
Meters
for more
per second.
video like this
They're a
and to
team.
motivate me to
The
make
math
these boring
and the units,
Aheshoth
they
videos.
always go together.